So that's a good news. I'm just going to go over this one more time, but add one level. Then on Monday, I'm going to add one more level. And then I'm going to evaluate. Are we ready? We're going to have a quick quiz. And the quick quiz will either be Tuesday or Wednesday. Just short with just 4.5. All right, so in the box it says, this is just what you did with your table talk. If a relation pairs element A of its domain to element B of its range, the inverse relation pairs B with the A. In other words, if A comma B is in the relation, then B comma A is in the inverse. If both a relation and its inverse happen to be functions, they are inverse functions. So let's look at example 1. Given the relation below, find its inverse. All right, so somebody tell us, what do you do to find the inverse? We just said this 3 times. What do you do? Yeah, tell us. Awesome. We're going to flip the numbers. And so what I want you to do when you're given a table, it's now x, and we're going to put the y inverse symbol. So this will be -1, 0, and you're just going to switch the x and the y values. All right, so that's the inverse. That simple. Now I'm going to ask you a couple of questions that go back to Unit 3. Is the relation is the original. Is this a function? Yes. How do you know? That's true. Yeah, Becca? Awesome. That's it exactly. So let's refresh our memory in case we need it, even though we did it yesterday. A relation is a function if each x value has only one y value. So write that down. This is how we know. A relation is a function if each x value has only one y value. Okay, so now the answer to our first question, is the relation a function? Yes, because each x has only one y value. So 0 only had one output, 2 has one output, 3 has one output, and 4 had one output. Now, I'm going to ask you about the inverse, our new table. When I look at that new table, is the inverse a function? Looking at this new table, is it a function? Yes. Okay, yes it is. I'm going to change colors so I can keep that together. So is the inverse a function? Yes. Hey, let's do what you guys do. Let me lasso that. So I'm going to duplicate and drag it. There we go. Have you ever done, like I'm starting to now when I'm using a paper, I'm trying to like tap my iPad on my paper. I was like, okay, I've really gotten into the technology now. Okay, so if the relation and the inverse are functions, what do we call that? 1-to-1. So if the original is a function and the inverse is a function, we call it 1-to-1. We learned this yesterday, so I'm just recapping what we did yesterday. We're going to do one more recap from yesterday before I take us into the new stuff. Example 2 says find the inverse of y equals x squared minus 1. So let's do that. So what do we do first? Davey? Good job. We're going to flip the x and the y. So we would write down x equals y squared minus 1. Now you're going to solve for this new y. So what's my first step? Yeah, Becca? Add 1. And then how do you undo a square? Square root. Now the problem is when I square root, I need plus or minus. When I do a square root to both sides, we're going to learn this more in the next unit, but I'm going to write it now like this. Y inverse is plus or minus the square root of x plus 1. So now, do you know how I keep making you do your arms? Do I keep doing that? I did that the other day. So it's asking me, is the inverse a function? So I want you to think about the original equation, y equals x squared minus 1. With your arms, what does that one look like, the original? It's a U shape, right? And what we talked about yesterday was something called the horizontal line test. If I draw a horizontal line through the original graph, that tells me whether its inverse is a function. So is the inverse a function? No, it fails the horizontal line test. So here's what I want you to kind of write down that maybe when you look at this later. So y equals x squared minus 1. It's a U shape. If I do the horizontal line test, tells me about the inverse of y. Let me repeat that. This is the new part from yesterday. If you take the original equation, the original graph, and you draw a horizontal line through the original, it tells me about the inverse. So, I would say, is the inverse a function? No, because it fails the horizontal line test. So, is it 1-to-1? No. The inverse has to be a function. No, the inverse is not a function. So again, example 1 and example 2 are a recap of what we did yesterday. Okay, this is what we did yesterday. So now I'm going to take it up a level, just a one new part, and then everything else is either practice or using this. We have something called composition of inverse functions. And it's interesting because I teach AP Calculus and we have been using this week. We have been using this particular concept. And it says this: if F and F inverse are inverses, then no matter which order I do, F inverse of F or F of F inverse of X, both compositions have to equal X in order for F and F inverse to be inverse. So this is a critical skill for future math classes. So let's look at example 3. I'm going to lead you through part A, then I'm going to pause and let you try part B. So it says verify that F and G are inverses by finding the composition of functions. So what this means is the following. I need to do F of G of X Well, g of x is x plus 7 over 2. Now, we did composition of functions in our previous unit, so you are supposed to remember how to do composition of functions. If you find that you are really shaky on that, that means you come in the mornings, you go to math lab. Don't wait till office hours. That's too late. Okay? Don't wait for office hours. but seek me out or seek out help, because you're now expected to know composition of functions. But if you're like, whoa, what are you doing? Then that's a deficit. That's something that we did not really learn then when we were supposed to. So f of x plus 7 over 2 means I go to f, and I'm replacing my x with this new input. And again, if you're looking at this like, what on earth are you doing? Then you have somehow either forgotten composition or we need a deeper refreshing. So now the 2's cancel, and I get x plus 7 minus x, which is x. Did you want to do this? Yeah, just see if you can find an empty chair somewhere. You can just sit anywhere, it's fine. There's one right there. All right, now I'm going to do the reverse order. This box says both directions have to equal x. Okay, both directions, f of g of x and g of f of x, have to equal x. So f of x is 2x minus 7. Now we go to the g function. G says the input plus 7 over 2. Here's my g function. The x represents the input, and my input is 2x minus 7. The 7's cancel, and I get 2x over 2, which is x. So I just verified it. So now, here's what I want you to do in letter B, and I'm going to pause and let you start this. You're going to do both directions of composition of functions. Again, if you're super confused about this, ask people at your table first. If somebody at your table can't help you, then raise your hand. I'll try to do a quick refresher, but you're supposed to remember what we learned. Supposed to stick. All right, I'm going to go ahead and start the one on the left. If I want f of g of x, that's f of 1/3 x minus 4. So now I go to the f function, and f says multiply 3 times the input plus 12. Okay, 3 times the input plus 12. When I distribute the 3, I get x minus 12 plus 12, which is x. That's perfect. That's what I wanted. Now I'm going to do the other side. G of f of x will be g of, and I put f of x in. That's 3x plus 12. Now I go to the g function, and it says take 1/3 times my input minus 4. So I get x plus 4 minus 4, which is x. I distribute that 1/3. 1/3 times 3x is x. 1/3 of 12 is 4. All right, so this is what was new. It's called the composition of inverse functions. And it says, if f and g are inverses, then both directions of the composition f of g of x and g of f of x have to equal x. That's the new layer today. Now everything else we do reviews yesterday and this, okay? Questions on example 3? All right, so let's look at example 4. It says graph the inverse for the relation shown. So here's how I do this. I call this x and y, and do you see there's dots on the graph? So what I do, if I have a graph and I want to graph the inverse, I pick as many dots as I see and I write them down in a table. Then what do we know about an inverse? You flip them. So I'm just going to make a new table. Whoops. I'm going to make a new table and call it x, y inverse. And then my points, I just flip them. Then let's plot these. Okay, so I'm going to plot 3, 2, 0, 1, -1, 0, 0, -1, 3, -2. So, and you can also imagine, remember how we talked yesterday that graphically it's a reflection over the line y equals x? Because you might wonder, like, how do you know which direction it's going? And so if you think about this piece here, this piece gets reflected over, this piece gets reflected over, this piece gets reflected over, and so on. Then I ask you, is the inverse a function? You have 2 methods, actually, if not 3 methods, to figure this out. You can either look at the table. You see that 3 has 2 different outputs. You see that in the table, that when x is 3 in the inverse, it has 2 outputs. I could also draw the vertical line through the inverse graph. It would fail the vertical line test. Or my third method is, I could take the original that's in black, and if I did the horizontal line test on the original, it fails. So the inverse is not a function, and you have 3 options. I'm going to say no, fails the horizontal line test. I could say fails the vertical line test, or I could say fails because when x is 3, it has 2 outputs. So any of those 3 reasons would be allowable. All right, questions on that one? Yeah. Absolutely, absolutely. Okay, so the question is the inverse a function? So do you see in the table, we can go back up to like one of the first examples. Do you see that when x is 3, it had 2 outputs? It's not a function. Now, I could also look at the original graph that's in black. And if I drew a horizontal line, it would fail the horizontal line test. Yes, yes, absolutely. All right. When the inverse of a function is not a function, you can actually restrict the domain so that it would be a function. So I want you to look back at example 4 that we just did. Look at this black graph, okay, the one that I have in black. How could I have chopped it so that it would have passed the horizontal line test? Can you think of a region where I could say, let's chop it right here and then it'll pass it? Yeah, Angelo? Yeah, right here. Do you see, if I chop the graph right in the middle, right through that vertex, and if I eliminated half of this, it would pass, right? Okay, so sometimes you can do that. So what I could do is I could say, well, if we let x be greater than or equal to 0, it would now pass it. So let's take a look at an example. It says, given the function f of x equals the square root of 2x minus 1 plus 3. So this is where it is super, super, super important that you remember all the parent functions that we've done and then what the transformations do. So when I have the square root of 2x minus 1 plus 3, remember the parent function. So if I have y equals the square root of x, okay, if I have y equals the square root of x, my domain was x was greater than or equal to 0, and my range was y greater than or equal to 0. So do you remember what we talked about yesterday? For domain of a square root, what's inside the square root can't be negative. Let me say that again. What we learned yesterday, when I want to find the domain of a square root, the inside can't be negative. It can be 0 and it can be positive. So you set the inside greater than or equal to 0. So we're going to add 1 to both sides and divide by 2. So my domain then would be bracket 1/2 to infinity. Any ideas on how my range is going to change? If you think about transformations, how would the range change if you think about it? Yeah, Angelo? It's been shifted up 3. So let's write ourselves a note. This one has the transformation of up 3. So instead of it being on the x-axis, okay, instead of my parent function that's on the x-axis, it has been shifted up 3. Now, I want to do something immediately from here. The domain and range of the inverse are the flip of the domain and range of the original function. So let's jump all the way down to letter D. If you switch the x and the y, what is the domain now of my inverse? Good job. 3, infinity. And what is my range now? Good job. 1/2, infinity. So remember how we switch the x and the y? Well, the domain and the ranges switch. All right, so let's find the inverse. You switch x and y in the original equation. Oh my goodness, now you can see the connection to what we did in the 4.1 to 4.3. You remember how we were solving radicals and like the 1/2 powers and all that? It was at the end of your homework from last night. So you switch x and y, and then we're going to solve for new y. So what's my first step here? Subtract 3. So I get x minus 3 equals the square root of 2y minus 1. All right, well, how do you undo a square root? You square it. So we're going to square both sides. So that's going to give me x minus 3 squared equals 2y minus 1. Then what do? Good job. You're going to add 1 to both sides. And then what's my very last step? Divide by 2. So this is going to be a sort of ugly looking inverse. So I'm going to say f inverse of x is that big, huge, ugly thing.
Did you say it was like 1/2 x squared minus 3 squared plus 1/2?
Okay, so let me write something down. Are you saying
We're gonna homework somehow if you're over this over 2 and you could just put them as like 1/2 x.
you can do that, but you can't do that here because x minus 3 squared, this is false. Do you remember we did a homework problem on this? Like, that's x minus 3 times x minus 3. So, like, what you're thinking is true, like this. If this had been x minus 3 over 2, I could have written that as 1/2 x minus 3/2. That's true. So I think what you were thinking is correct. The problem is this does not, x minus 3 squared is not x squared minus 3 squared. It is. That's x minus 3 times x minus 3. You do all that foiling. So just be careful with this. Okay? You cannot do that. Mm-hmm. All right, so now, is the inverse a function? Well, let me back it up because I'm not all the way done with finding my inverse. Do you see, and this is why I wanted us to do part B first. Do you see that the domain is not all real numbers? You see that domain is not all real numbers. But on this one by itself is all real numbers. But because I have a square root, and that square root represents a parabola on its side, and I only have the top half of it. So, I mean, this is why it's so important that we did those transformations. Okay, this is really, really important, and I'm trying to go nice and slowly here. Is that this domain is 3 to infinity. So I only have the right half of this parabola. And when we go to graph it, this will make a lot more sense. So is the inverse a function? The answer is yes. It'll pass the horizontal line test on the original function. So let's go ahead and try to make sketches here. So on f of x, you remember how we said the domain was 1/2 to infinity? If you plug 1/2 in, that's 2 times 1/2 minus 1 plus 3. What happens underneath that radical when you plug in 1/2? Just under the radical. What's 2 times 1/2? 1. What's 1 minus 1? 0. 0 plus 3 is 3. So I'm going to have to go halfway and put a 3. Let's try What if I try x is 1? What if I try x is 1? 2 minus 1 is 1. The square root of 1 is 1. 1 plus 3 is 4. Now this is kind of tricky. I need a 5 halves here. Because the next nice number under a square root is 4. So I kind of did some guess and check here. 2 times 5 halves, the 2's cancel. I get 5 minus 1 is 4. Okay, the 2's cancel. I get 5 minus 1 is 4. Square root of 4 is 2. 2 plus 3 is 5. So I'm going to go to I need my 1 comma 4. And then 2 1/2, 5. So this is my square root this way. Then guess what? Now I did the hard work. Okay, I did all the hard work already. To do the inverse, I'm going to switch those. So I'm going to go 3 1/2, 4 1, 5 is 2 1/2. And I need you to be mindful that inverses are a reflection over the line y equals x. So I want you to imagine when you do that first one, so we know what the square root looks like, you're reflecting it over that line y equals x. All right, so that was pretty tough. Okay, that was pretty tough graphing there. All right, let me ask you this. I put an extra example. This says, are the functions f of x and g of x inverses of each other? Use compositions to explain. So here's what I mean. You're going to do f of g of x, and you need to do g of f of x. You want to compute both of them, and they should both turn out to be x. So let me give you a head start on me. This was the big idea today. Just while I'm trying to be patient. On tonight's homework, there's 2 problems at the end that I called challenge problems. Those are optional, but I have some of you that are pretty advanced, and I do not always feel like I'm giving you all the challenges that you want or need. So I put those at the end, and again, they're optional, but they're kind of fun to work out if you want to look at those. All right, I'm going to go ahead and start f of g of x. This is f of, I do not know why I wrote that. Let me try that again. I want f of g of x, which is f of the square root of x over 3. Now I go to f. F says, take 9 times the input squared. Okay, f of x means 9 times the input squared. So the square root of x squared is x. 3 squared is 9. So you can see the beauty of those exponent properties. Yeah, Davey, did you have a question? Do you see f of x? This says 9 times x squared. Yeah, that's what that is. Now the 9's cancel, and I get x. Any other questions on this half? All right, let's do the other direction. I have g of f of x. Now, do you notice, in case maybe this was the question, there's no parenthesis around the 9 with the x. So it's not a 9x, the quantity squared. If they meant that, there'd be parentheses. So it means 9 times x squared. So let's make sure we're understanding that component. Now I go to g. G says take the square root of your input divided by 3. Again, g of x is saying take the square root of my input divided by 3. That's 3x over 3, which is x. So I just verified it.